Continuing the basic semiconductor physics of solar cell, photovoltaic cells cells use semiconductor materials to convert the sunlight into electricity. So the sunlight energy that is converted to electrical energy by using semiconductor materials. Photovoltaic devices are the semiconductors in pure crystalline silicon form, that is tetravalent. Silicon is having outer shell 4 electrons. Therefore, photovoltaic devices are semiconductors in pure crystalline silicon forms. Elements that play important role in the photovoltaic devices are silicon, boron, phosphorus, gallium, arsenic, cadmium, and tellurium. Gallium and arsenics are used in gallium arsenide solar cell, while cadmium and telluriums are used in cadmium tellurium solar cells. Silicon is the intrinsic semiconductor used in the photovoltaic cell. Therefore, this is the atomic structure of silicon, in which there are 14 electrons, that is outer shell 4 electrons, 2 plus 8 plus 4 electrons. 14 is the number of electrons and 14 protons and 14 neutrons as the. Therefore, this is the atomic structure of a silicon atom, in which that is represented as, this is a representation of the same thing. Outer shell there are 4 electrons, and silicon element, this, since it is a 4 electrons, to make 8 electrons outer shell, covalent bonds are formed. For between the atoms there are covalent bonds are formed in order to make the outer shell 8 electrons. Therefore, this is the structure of the element, silicon element, and this is the atomic structure of a silicon. Therefore, silicon is the semiconductor used in the photovoltaic cell. Now, continuing the basic semiconductor physics of the solar cell. To increase the conductivity of the intrinsic semiconductors, controlled quantities of specific impurity atoms like boron, which is a trivalent, therefore the valency outer shell is equal, outer number of electrons valency is equal to 3. That is for the p-type material, p-type semiconductor. And phosphorus, let's say, which is a pentavalent, that is 5 valency electrons in the outer orbit, that is for a n-type material. They are added to the silicon to make the extrinsic semiconductors. Therefore, if you are adding the impurities into the intrinsic semiconductor or in the silicon, either boron to make n-p-type, phosphorus to make n-type, then that material we call it as extrinsic semiconductor. And this process is known as doping. That is, adding the impurities into an intrinsic semiconductor and converting into an extrinsic semiconductor. That process we call it as doping. Therefore, the trivalent impurity atoms, that is outer shell number of electrons equal to 3, that enters the semiconductor lattice and becomes electrons acceptor, and that side, that is known as holes. For to make a p-type material in which holes are the majority carriers, and these holes, which are effectively positively charged, to move through the material as free carriers. Such a material is called p-type material. Therefore, if you add a trivalent impurity like boron is added to a pentavalent silicon semiconductor, then there will be holes are there that are majority carriers, and electrons will be the minority carrier. Such a material is called p-type materials, having holes as the majority carriers and electrons as the minority carriers. Now, coming to p-type semiconductor, as we are seeing, p-type semiconductor, in this silicon is doped with a trivalent element such as a boron, and these dopant atoms forms a covalent bond with the adjacent silicon atoms in the crystal. For in this can we can see that one, the boron, which is a trivalent, that is added to the silicon silicon element, in which we can see that one, since the outer shell 3 electron, there is a hole is there. Therefore, to this hole, the electrons from other outer one that comes into the holes, so that the holes will be moving. That is, in p-type materials, trivalent, that is trivalent acceptors contribute movable positively charged holes leaving rigid, immobile, negative charge in the crystal lattice. Therefore, the holes can move, mobile one, and immobile is the negative charge. For p-type material is called acceptor, since it accepts the electrons, because holes can accept the electrons. That is why p-type material is called acceptor. Coming to a n-type semiconductor, similarly, when a pentavalent impurity is added, just like like a pentavalent impurity means phosphorus. If you are adding a phosphorus into a silicon material or added to a n-type material results, which has electrons as the majority carriers and holes as the minority carriers. Therefore, when a pentavalent is added into a intrinsic material like silicon, then it makes a n-type material, because electrons will be the majority carriers and holes will be the minority carriers. These dopant atoms forms a covalent bonds with an adjacent silicon atom in the crystal. Therefore, this is the structure of that one. In a covalent bond is formed, in which we can see that one, since outer shell is having a 5 electrons, the pentavalent, 1 electron is free to move. Therefore, that's what's called mobile one. That negative charge is mobile and positive holes are immobile one. Therefore, in a n-type material, pentavalent donors contribute movable, negatively charged electrons, leaving rigid, immobile positive charge in the crystalline lattice. Therefore, in n-type material is called donors, since it donates the electrons. It can donate this. Can donate the electrons. That is why this is called a n-type material. Therefore, in n-type material, majority carriers are the electrons and the minority carriers are the holes. Continuing the basic semiconductor physics of solar cell, silicon's conductivity even at normal temperature is very low, and so it is referred as a semiconductor. As we will see that by adding a minute quantities of the impurities, the conductivity of the pure or that intrinsic semiconductor can be greatly increased. That is why by doping either trivalent material or a pentavalent, the conductivity can increase, and the energy that an electron must acquire to jump across the forbidden band from the valency band into the conduction band is called band gap energy. That's designated as Eg. For a silicon, the energy required to emit an electron from the valency band into the conduction band through the forbidden band, the energy requirement is 1.12 electron volt. Therefore, in a solar, energy is passing in this one. If photons are passing, hitting this one, that energy, if that is more than 1.2 1.12 electron volts, then that outer shell the electrons can be emitted. Therefore, that's a picture showing that as photons comes here, hitting this one, the electrons can be liberated. Coming to the construction of a solar cell is basically a junction diode, although its construction is a little bit different from the conventional PN diode. In that one, a solar cell, that, as you know, that consists of a PN junction with large surface area, and the n-type material is kept very thin. That is a n-type material, that is thickness is very low, that is very thin to allow the light to pass through the PN junction. Very thin layer of n-type is grown on a relatively thicker p-type semiconductor. This is a thicker one p-type, likely or thin layer of n-type is grown, and then a few finer, very small electrodes are provided on the top, that is n-type and p-type semiconductor. Electrodes are provided here, and then when they connected through a load, through a conductor, then electrons will be moving, and then the current will be moving, electrons will be opposed to that one. Therefore, this is the conceptually, this is a n-type material which is thin material, and p-type is relatively thickness is more here, and here the light, there is a its contact is the therefore this is the construction of a solar cell. Now let us see a PN junction. A PN junction means a p-type material is the in which holes are the majority carriers, electrons are the minority carriers, And N-type material, electrons are the majority carriers and holes are the minority carriers. Therefore, these are the two, P material and N-type, they are joined together. And when a PN junction is first formed, there are the mobile holes on this side and on P side and mobile electrons on the N side. Now, as they migrate, for the mobile holes will be migrating towards here and mobile electrons will be migrating towards here, towards P side. As they migrate across the junction, an electric field will be building up or that builds up and quickly, and then then it stops, the diffusion will be stopped, that one. Then electric field will be produced, that is electrons will be coming to here and holes will be coming to here, and electric field will be produced and further diffusion is being stopped here. Therefore, this is, we call it as an electric field, that is this layer we call it as depletion layer. Continuing the working of photovoltaic cell, light travels in packets of energy called photons. That's called the photons, which is a packet of energy. And the generation of electric current happens inside the depletion zone of the PN junction. That is depletion zone that has this, light energy falls. Here the current, the electric current will be happens inside the depletion regions. And the depletion region is the area around the PN junction where the electrons from the N-type silicon have diffused into the holes in the P-type material. Electrons are diffused here and to the holes material. And when the photon or when the light energy falls on this depletion region, when a photon of light is absorbed by one of these atoms in the N-type silicon, it will dislodge an electron, creating a free electrons and holes. An electron will be liberated and a free electrons and holes are generated as light energy falls on the depletion region. Now, if a wire is connected from the cathode, that is from the N side, to the P side, a wire is connected to silicon, electrons will be flowing through the wire. Electrons will be flowing through this wire when a wire is connected from the N-type and to the P-type. That is because as light falls here in the depletion region, electrons will be emitted and that is free to move this one. That will be moving towards this one, that causes a current through the load. Continuing the working of PV cell, as we have seen, it's a PN junction. This is a depletion region and electric field is produced at this junction and light energy is falling on this depletion region. Therefore, consider a figure shown below in a PV cell made up of silicon and a resistive load is connected across that one. A resistive load is connected across the PN junction. And the PV cell consists of P and N-type layers of the semiconductor, P-type semiconductor and N-type semiconductor. And these layers are joined together to form the PN junction. A PN junction is formed at this point. And the junction is the interface between P-type and N-type material. P-type and N-type material, this is what we call it as junction of that one. And when light falls on this junction, when light falls on that one, the electron starts moving from one region to another. Electrons will be moving from this side to this side. That electrons will be moving here and that will be causing a current through the load. For as light energy falls on the depletion region, electrons will be liberated. That goes to move through the load and a current will be flowing through the load, which is connected between P-type material and N-type material. Therefore, in that one, light energy, that is sunlight energy, is being converted into electrical energy. That is done in a PV, photovoltaic cell. Continuing the working of photovoltaic cell, it is very important to know that all the hitting photons cannot release an electron from the atoms to become charge carriers. All the photons cannot charge. But the photons with a short enough wavelength and high enough energy can only cause an electron in the photovoltaic material to break and free the atom. That electrons can hold free from that bond only if it has got enough wavelength and enough energy, that one. Therefore, generally, the term solar cell is reserved for the devices intended especially to capture the solar energy from the sunlight, while the term photovoltaic cell is used when the source is unspecified. If the source is specified, we call photovoltaic cell. But if the source is solar energy also, then we call it as sunlight, which is called solar cell. Therefore, this is, as we have seen already, the solar cell structure as such. There is a N-type material, P-type material, and when light falls on the depression region, electrons are emitted, and that causes a current flow through the load, which is connected between N-type material and P-type material. Continuing the photovoltaic cell, in this one, as we have seen here, it's a N-type material and a P-type material. Depression layer is formed, and when photons are hitting the depression region, electrons are emitted, and if we are providing a path to that electrons to flow, then it is connected between the P-type material. The electrons will be flowing through the load, therefore current direction will be opposite to the electron flow, and as the electron reaches to here, that will be recombined with the holes in the P-type material. Therefore that way there will be a current flowing through the load. Therefore when electrons flow from the N-side contact through the load, electrons are flowing through that one and back to the P side, where they recombine with the holes. They recombine the electron that is flowing from the N side, that is back coming to here and recombine here, and that causes recombine the holes. Conventional current I in the opposite direction. Therefore, the electron is flowing from the N-type material to the P-type material. That will be recombined with the P-type material in the holes in the P-type material. Therefore, electron flow is in this direction. That will be causing a current in the opposite direction. Therefore, the light energy is being converted into electrical energy in the PV cell, photovoltaic cell.